We close it. We dump the ions out at extremely high speed with no resolution or no mass accuracy. And we count the number of ions. Okay. I take that pre-scan signal. Ooh, that's a type error right there. AGC. Okay. I ratio that to the number of ions you asked me to put into the trap. That's your AGC target value. And I determine a new ion time, a new injection time. So let's say you wanted 30,000 ions in the trap. You have a very large peak eluting and you put 300,000 ions into the pre-scan. How far off are you?
Tenfold.
Tenfold.
So 10 times shorter.
So what we do is then we refill the trap for the real data collection 10 times shorter, or not 1 millisecond but 0.1 milliseconds. And how many ions do we put into the trap? 30,000. And we collect the spectra with the proper mass accuracy and the proper resolution. Okay, does that make sense? Now, so that way you can be quantitatively correct, we then reverse fudge the numbers. When we show you a spectra, we change the peak heights. We take the real number of ions at that particular mass you measured, and we multiply it by the inverse of the injection time we actually calculated. And we bring the peak heights back up. So every ion you see in this spectrum is a figment of the computer's imagination. And it's good enough quality that we can quantitate over several orders of magnitude. Does that make sense? How many ions are in every single scan on the linear ion trap?
The AGC.
30,000. The AGC target value.
Sometimes you have limits on the injection.
Right. You can set upper limits, so you never overfill. You can cause it to underfill.
That's right. If there's not much going on.
You got it. Does this make sense?
So
Do you have questions?
What is the injection?
The injection time is how long the gate is open?
Right. How long the gate is open to fill the trap. Okay, and that will change from scan to scan to scan. Every scan will have a slightly different injection time. Okay. Intense ions will have what kind of injection times? Short. Very tiny ions will have very long injection times. Okay. Now, which do you prefer? You prefer short injection times. Why?
Since we can get fewer thin ions.
Because then we do have more signal.
Well, you have more signal. By having more signal, we can scan faster. So the more intense the ions are, the faster we scan, the more time we have to dig down into the grass. Okay. The problem is when we dig down in the grass to find your real small guys, then we take long times to do that, and we get less number of MSMSs per chromatographic run. Okay. So our trade-off is we either can be very sensitive with a lot less peptides found, or we can miss the small guys and get a lot more scans of the big guys. That's your trade-off always. Does that make sense? Okay.
So you can stuff more ions in the FTICR.
Right. We're going to talk about those injection times a little later.
Are those numbers directly comparable? So that's physically the number of ions, truly the number of ions?
In the linear trap, yes. In the FT, no.
It's an estimation of some sort.
Right. And I'll give you some rough numbers when we get there. Do you guys need a break? Do you need a 5-minute break?
Eventually we'll have lunch. What time is it?
I don't know what time. I don't wear a watch. That makes customers always feel weird when I'm looking at my watch.
11:46.
Oh, so we'll just work another 15 minutes and we'll take a break?
That sounds good.
Okay. What we'll do is we'll get the LTQ covered, then we'll take a break and do the FT after lunch. Okay, now. So that what we've just accomplished allows us to accomplish a full MS spectrum to see what peaks are eluting. What's the next step we want to do?
Blow it apart.
We want to blow them apart. We want to do fragmentation. The first thing we do is we do isolation. We purify and get rid of all the other ions that are eluting except the ion of interest. Okay? The way we do that is we apply a dipolar field to the X rods, ejecting every ion but the ion of interest. So if this is the ion of interest, okay, we know his frequencies because we know his mass. We apply to the
Across all the others?
right. We apply to the
So you're actually changing the amplitude of the dipole?
not the amplitude, the frequencies.
The frequencies.
So what we do is we apply every frequency of all the ions higher in mass and every frequency of all the ions lower in the mass to the rods all at one time. And those ions go, and the ion of interest is never in resonance, so he just sits there.
How can you do that without scanning? How can you do it all at the same time?
Imagine playing a piano. If you hit one note, how many frequencies you hear? One. If you hit a chord, you hear all the frequencies at once. That's what we do, is we play a chord on the synthesizer. Okay? And what it's really weird.
What does it look like? Is it just like a dark big line, basically? Or?
Give me a sec, I can... So there's one. What you get when you combine these two is...
Oh, yeah, I remember that from physics. Yeah. But if you had all those possible things, it would
And what you end up...
folded. Yeah.
It looks ugly.
Where it's somehow missing
Just one frequency.
whatever you're tracking.
You set the number of frequencies that's missing by setting the isolation width.
So that's how you can do the pseudo MS3.
Right, so when you set the isolation width, you're setting how many frequencies do I get rid of.
How does it do pseudo MS3? Because that requires the phosphate to drop off, but
So what it does is, with the pseudo MS3rd, they calculate where the phosphate would be,
Right.
and they remove those frequencies too.
to produce that ion, it causes you need to fragment.
So,
the original
yeah, the precursor fragments, and those frequencies aren't being used, they're there, but there's no one to hear them. The minute he fragments and produces it, then those ions hear the frequency and they fragment again. Okay. Now, this is at 160 volts. So this is not a little kick. This is a whack. Those ions are gone.
So
Okay.
typically you were talking about a 1 volt.
1 to 15 volts dipolar. This is 160 volts. These ions are whacked hard and they're gone. It's clean. Okay.
They're X.
Yep, they're X-axis ejected. The detectors are turned off. Okay, now, just fly right past me and hit the walls of the manifold. Now, we're going to fragment him now. This is fragmentation, resonance excitation. It's also, if you got your PhD on the West Coast, it's collisionally induced dissociation. If you got your PhD in mass spec on the East Coast, it's collisionally activated dissociation. If you work for thermo, it's called the tickle voltage. Okay. Now, how many ions are in the trap?
Well, however many were there.
Of how many different masses, I should say?
Well,
One.
one window
Right. How many frequencies, hence, are in the trap?
should be.
One. So now we take, to the dipolar, to the X rods again, we take the frequency of the ion of interest. Before we left him out, we took every other frequency. Now we just take his, we apply it to the X rods, this time maximum 5 volts. So the difference between isolation and fragmentation is the power. Isolation was 160 volts. The unwanted ions are just blown out of the trap. This guy is max 5 volts. So when you type in a collision energy of 35%, you're saying give me 1.7 volts of X rod excitation. Now, put your hands up. You don't have to move, just put them up. Okay. 160 volts is this. They just hit the side of the manifold. Okay. For a normal peptide mass, we use about 7 or 8 volts, and he does this for ejection. He's just barely beyond